Third overtone. Now how do you even decide which overtone is which harmonic? Hey, are you one of those who find it difficult to decide which overtone is which harmonic? Then worry not. This video is for you. In this video, we'll go into the details of this topic, and by the end of this video, we'll surely put a full stop on this confusion. So let's get into it. So in order to clear our confusion on this topic, we just need to understand this simple concept over here, a concept or a trick as you might call it, okay? So we are supposed to understand this table over here, and if we are able to understand this table, we'll be able to solve the problems based on organ pipe very easily. The problems will become a cakewalk for us, okay? So let's go through this table, let's try to understand this, okay? So the first column says types. Now there are two types of organ pipes, you might know it. They are open and closed, right? So an open organ pipe is one which is open at both the ends, and a closed organ pipe is one which is closed at one end, okay? It is closed at one end, okay? Now coming to the second column, fundamental frequency. Again, you'll know this comes from derivation. Today we are not going into the derivation of this thing, okay? It can be looked up in book. Okay, our main objective over here is to clear the confusion between this, right? Which overtone is which harmonic, okay? But anyways, we'll need this for problems. So fundamental frequency of an open organ pipe is V by 2L, and that of a closed organ pipe is V by 4L, okay? Where V stands for velocity of wave. In our case, it's the sound wave, right? So velocity of sound, and L stands for their respective length, okay? Length of the open organ pipe, length of the closed organ pipe, okay? So far so good, okay? So let's come to the important part now, okay? You have to understand this in order to clear the confusion between overtone and harmonics, okay? So now in third column we have harmonics present. Now what are the harmonics that are present in open organ pipe? Okay, so harmonics present in open organ pipe. We have all the harmonics present. Okay, so all the harmonics 1, 2, 3, 4, all of them are present in open organ pipe. Okay, let's come to the closed one. Okay, we'll keep this at the back of our mind. Okay, so in case of a closed one, only the odd ones are present. Okay, so only 1, 3, 5, 7, 9, only the odd ones are present, only the odd harmonics are present in case of closed organ pipe. Okay, again this comes from derivation. Okay, we need not worry about that. Okay, we are just supposed to remember this at the back of our mind. So in an open organ pipe, all the harmonics are present, all of them 1, 2, 3, 4, 5, 6, all the integers. And in case of a closed organ pipe, only the odd ones are present, 1, 3, 5, 7, 9. Okay, now let's understand this. Okay, let's understand which overtone is which harmonics. Okay, we are supposed to use it in problems, right? So let's choose a general overtone. Okay, let's choose some general integer n. Okay, so nth overtone. Okay, in case of open organ pipe, nth overtone just means n plus 1 harmonic. Okay, because if you see, all the harmonics are present, right? So nth overtone will just mean n plus 1 harmonic, the immediate next one. Okay, so if we have first overtone, it just means 1 plus 1, which is 2, right? Nth overtone means n plus 1 harmonic. Again, if we have second overtone, it just means third harmonic, the next number. Again, the third overtone means fourth harmonics. Fourth overtone means fifth harmonics. Sixth overtone means seventh harmonic, right? Just increase it by 1 plus 1. So in general, nth overtone means n plus 1 harmonic, right? And that is in the case of open organ pipe. Now coming to a closed organ pipe. Now it is a little bit tricky, as you can see. So now again, if we have nth overtone, okay, in a general way, if we have nth overtone, first, second, third, any number, okay, in general n. So nth overtone means 2n plus 1th harmonic. Why did this happen? Because if you see, the harmonics present in an closed organ pipes is only the odd ones, right? So only the odd harmonics are present in case of closed organ pipe, and this is the general format for a odd number, right? 2n plus 1. 2n is an even number, plus 1 makes it odd, right? So only in order to keep the harmonics odd, it should be of this format, right? So, or you can say 2n plus 1 is odd, so only the odd harmonics are present in case of closed organ pipe. Or basically you are just supposed to remember this relation, right? Nth overtone means 2n plus 1 harmonic. Again, why did this happen? Because only the odd ones are present. We don't have the even ones, okay? So you cannot say n, suppose the value of n is 1, okay? So first overtone in case of closed organ pipe, it won't be second harmonics, because second harmonics is not present, it's even harmonic, right? It will be 2n plus 1. So in place of n, we chose the value as 1. So substitute 1 over here. So 2 ones are 2 plus 1, which is third harmonic. Okay, so the next odd number, right? So first overtone will become third harmonic. Second overtone, in place of n, you substitute 2. 2 2s are 4 plus 1, fifth harmonic, the next odd number, right? Again, in place of, suppose we say third overtone, 2 3s are 6 plus 1, seventh harmonic. So again, the next odd number. Again, if we say fourth overtone, that will be 2 4s are 8. In place of n, just substitute 4. 2 4s are 8 plus 1, 9, right? So that will be the ninth harmonic. I hope the idea is clear. So this is how you relate between the overtone and harmonics in case of open and closed organ pipe. Okay, so for let's summarize. For an open organ pipe, it's just plus 1, right? You just take the overtone and add 1 to it. Okay, so first overtone, second harmonic, second overtone, third harmonics, third overtone, fourth harmonic, just add 1. Okay, in case of closed one, in closed one, we know that only the odd ones are present. Okay, so first overtone does not mean second harmonic, it means the odd number, right? Third one, right? It will be third harmonic. In place of n, you put 1, 2 ones are 2 plus 1 3. Okay, so third harmonic. So first overtone is third harmonic in case of closed organ pipe, because only the odd ones are present. How many times am I going to repeat this? Anyways, okay, now any frequency through this organ pipe can be represented in this format: f dash equals n times f, where n is the number of harmonic. Okay, remember that n is the number of harmonic. This formula we are going to use it in problems. Okay, and f here is the fundamental frequency. Okay, any one of this, depending upon whether the organ pipe is closed or open. Okay, so we'll use this in formula, but before we go to the questions, let's quickly revise which overtone is which harmonics in the next chapter. Okay, let's try to put in action what we have learned so far. So here we have different overtones: first, second, third, fourth, fifth, sixth, and we will try to find the harmonics for each of this for open and closed organ pipe. Okay, so let's start. So first overtone for open and closed organ pipe. Okay, so basically the question is first overtone equal to what harmonic? Okay, first overtone equal to what harmonic in open and closed organ pipe? Okay, so let's decide. So first overtone, if you see an open organ pipe, okay, open organ pipe says that all harmonics are present, and nth overtone means n plus 1th harmonic, right? So basically you add 1, right? So first overtone means second harmonic. So in case of open, it just means that it is the next harmonic. So first overtone, second harmonic. Now let's come to the closed one. Closed one says that only odd ones are present. So you cannot say it will be just plus 1. It will be the next odd number, right? Or you can use the formula 2n plus 1. Nth overtone means 2n plus 1 harmonic in case of closed one, right? So in place of n, you'll put 1, okay, plus 1. So 2 ones are 2 plus 1, that will be third harmonic. Okay, now let's come to the second one. Okay, you can try it side by side. So for open and closed one, okay, so again the question remains the same: second overtone equals what harmonic? Okay, so for open one, you can see that it will be the immediate next one. So second overtone means third harmonic, right? N plus 1, and here it will be 2n plus 1. So 2 into 2 plus 1, right? In place of n, just substitute 2. 2n plus 1, and in place of n, substitute 2. 2 2s are 4 plus 1, 5. Fifth harmonic, right? The next odd number. Okay, now let's come to the third overtone. You can try it yourself, open and close. A third overtone means fourth harmonic for an open organ pipe, the next number, right? And for a closed organ pipe, you are supposed to use the formula 2n plus 1. 2 into 3, sorry, third overtone, right? So 2 into the number of overtone plus 1. 2 3s are 6 plus 1, 7. So seventh harmonic, right? Let's come to the fourth overtone. You can try it out yourself. You can speed run it, okay? So fourth overtone means fifth harmonic in case of open organ pipe, the next one. And the closed organ pipe, 2 5s are 10 plus 1. That will be, I think, I did some mistake. Okay, 2 4s are 8 plus 1. Okay, 2 4s are 8 plus 1. That will be 9. Okay, so you can see the odd numbers over here, right? 3 5 7 9. Whereas in case of an open organ pipe, all the harmonics are present. So you can see 2 3 4 5. So similarly, going by the pattern, you can see here it will be sixth harmonic, and closed organ pipe, the next odd number, 11th harmonic. Okay, and here also you can do it by the formula as well, but you'll get this answers. Okay, sixth overtone means seventh harmonic or the next number, and here it will be the next odd number. Okay, so it will be 13th harmonic. Okay, or 2 into 6 plus 1. 2 6s are 12 plus 1, 13. Right, so I hope you were able to understand this, and if you were able to understand this, we are all ready for the problems. Okay, so let's try out some questions now. Not much, only one or two maybe. Okay, so let's go to the questions now. So question 1 over here, let's try to do it now. Okay, so now before we do it, I just want to tell you one thing. Let's just revise the formula that we learned. Okay, it says any frequency of any harmonic can be represented in terms of your fundamental frequency, right? F dash is n times of f. F is the fundamental frequency, n is the number of harmonics. Okay, so just remember this. Suppose if I tell you to represent, okay, or write third harmonics in case of an open organ pipe in terms of its fundamental frequency. Okay, write third harmonic in case of an open organ pipe in form of its fundamental frequency. How will you write it? You'll write it as F3. Okay, F dash, basically the third harmonic, the frequency of the third harmonic is given as n is the number of harmonic, third harmonic, and f is the fundamental frequency. Now in this case we have open organ pipe, right? So V by for open one, it is V by 2L. So this is how you write the third harmonic frequency for your open organ pipe. Okay, I want you to remember this. I want you to remember this formula. Okay, anyways, let's keep that aside. Let's read the problem now. Third overtone of a closed organ pipe is in unison, or basically it has the same frequency as the fourth harmonic of an open organ pipe. Okay, so you are supposed to find the ratio of LC by LO. Okay, you are supposed to compute this ratio. LC is the length of the closed organ pipe and LO is the length of open organ pipe. Okay, compute that ratio. So the question says third overtone of a closed organ pipe. Okay, so what is the third overtone of closed organ pipe? Okay, what harmonic? Okay, third overtone means what harmonic for a closed organ pipe. So if we see in a closed organ pipe, we know that only the odd ones are present. So we are supposed to use 2n plus 1, right? So third overtone, in place of n, substitute 3 plus 1. 2 3s are 6 and plus 1, 7. So we can write this seventh harmonic, right? This third overtone means, now we know that third overtone means seventh harmonic. We calculated it over here, right? So third overtone is seventh harmonic. Now seventh harmonic, we can write it in this terms, right? So we can write F7, right? We can simply write it as 7 times the fundamental frequency, right? N times F, right? 7 times the fundamental frequency of a closed organ pipe, right? And this is in unison, this is equal to the fourth harmonic of an open organ pipe, which basically means this is equal to the fourth harmonic. Now no overtone is given, so we need not convert it, it's given in simple terms, right? So fourth harmonic times the fundamental frequency of open organ pipe. Okay, so you can read it this way: the seventh harmonic or the third overtone, which is in fact the seventh harmonic of a closed organ pipe. So this is the 7 times the fundamental frequency of the closed organ pipe, is equal to the fourth harmonic of an open organ pipe. So the fundamental frequency of an open organ pipe. Okay, so now let's substitute the values, put in the formula for fundamental frequency of a closed organ pipe, which is V by 4L, right? And here it will be, here it's the length of the closed organ pipe. Okay, we are denoting it by LC, and 4 times the fundamental frequency of the open organ pipe, which is V by 2L, and length of the open organ pipe. Okay, V will cancel with V. Okay, basically the speed of sound in both the organ pipes will be the same, and here can you cancel something? We are supposed to find LC by LO, so we can cancel this, and you'll see that LC by LO, okay, LC by LO, okay, you can take LC to the other side, bring 2 over here, will be 7 by 8, right? 4 2s are 8, you can take LC over there, bring 2 over here, so 7 by 8, 4 2s are 8, right? So 7 by 8 is the correct answer over here. Okay, I hope this was very easy to understand. Okay, we just decoded what this third overtone means. Okay, we use this formula n times of f. Okay, so third overtone frequency equals third overtone, right, or seventh harmonic frequency equals 7 times of the fundamental frequency. So 7 times of the fundamental frequency in case of closed organ pipe, and here also fourth harmonic in case of open pipe, so 4 times the fundamental frequency of the open pipe, okay, open organ pipe. Okay, so remember that this N stands for harmonic and not overtone. So every time you encounter this word overtone, just convert it to harmonic, okay, in order to apply this formula. So let's move to the next question now. So question 2 over here, let's read it. Open organ pipe has a fundamental frequency of 300 Hertz. Okay, so the fundamental frequency of an open organ pipe is given over here. So let's read it further. The first overtone of a closed organ pipe has the same frequency as the first overtone of an open organ pipe. Okay, so this frequency, the first overtone of closed organ pipe, is equal to the first overtone of an open organ pipe. Okay, so now first of all, let's convert this overtones to harmonics, right? Because that is what we are comfortable with, right? And that is how our formula is, n times f, right? So let's convert this one. So the first overtone of a closed organ pipe, okay, so it's a closed organ pipe, which means only the odd harmonics are present. So we are supposed to use 2n plus 1, right? So in place of n, first overtone, so in place of n substitute 1. Excuse me. So 2 1s are 2 plus 1 3. Okay, so it's the third harmonic. So again we can read the question. The third harmonic of a closed organ pipe has the same frequency as the first overtone of open organ pipe. Now let's convert this to harmonics. So for an open organ pipe, we know that it's just n plus 1, right? So nth overtone means n plus 1 harmonic, because all the harmonics are present. So we'll use n plus 1, right? So first overtone means second harmonic, simply second harmonic, right? So again you can read the question. The third harmonic of a closed organ pipe has the same frequency as the second harmonic of an open organ pipe. Now this is so simple, right? So third harmonic of closed organ pipe, you can write it as 3 times 3, so n times f, right? So n times the fundamental frequency of the closed organ pipe. So 3 times the fundamental frequency of the closed organ pipe equals 2 times, so is equal to the second harmonic, so 2 times the fundamental frequency of the open organ pipe. Now we already know that the open organ pipe has a fundamental frequency of 300 Hz given in the question, and in place of the fundamental frequency of the closed organ pipe, we can substitute our formula V by 4L, right? Okay, and here we have 2 into fundamental frequency of the open organ pipe, which is 300. Okay, so this and this can get cancelled as 100. And what do we have now? The velocity of the sound, it was given in the question, sorry for not mentioning, it is 330 meters per second. Okay, so in place of V you can substitute 330 meters per second. Now we are supposed to find L, right? Length of the closed organ pipe. Okay, so length of the closed organ pipe will be given as 330 velocity of the wave divided by 2 into 100. Okay, so 2 and 4 we have. So 4 2s are 8, 8 into 100. So 8, 4 2s are 8 into 100. So this and this can get cancelled. So basically 33 divided by 80, right? So I think it's close to 41 centimeters, right? So the answer will be 0.4125, I guess, right? So this is in meters. Okay, so the answer that you'll get after calculating is 41, so close to 41. Okay, so there was one option which says 41 centimeters. You are supposed to tick it. By the way, it's a question from ACE series, which means it's a question from BITSAT 2011. Okay, so yeah, the answer over here is 41 centimeters. Okay, I hope you got it correct if you tried it. And that's pretty much it for today's class. I hope you were able to understand, grasp this idea, and your confusion is cleared. Go ahead and practice more such type of questions. Okay, so yeah, that's pretty much it for today. I hope you enjoyed today's class. If you did, smash like, subscribe. I'll see you soon in the next video. Till then, keep enjoying physics.